Good morning, everyone. So, we are discussing about the surfactant mediated separation processes, and we have come to the last topic of them. So, we started with the cloud point extraction, then we moved on to micellar enhanced ultrafiltration. Now, we are studying the liquid membranes. Now, as we have discussed in the last class, the liquid membranes, we have talked about the fundamentals of the liquid membranes and how the things will work, and we have looked into the types of transport those will be occurring into the liquid membrane processes. One is the type 1 of facilitation and type 2 of facilitation. The main difference between these two types of facilitation processes is that in type 1 facilitation there is a chemical reactant that will be present in the internal phase. Okay. So, the solute will diffuse through the oil phase from the bulk phase to the oil phase, and then it will move into the internal phase, and the internal phase will be having a reactant that will immediately react with the solute, and therefore, its solute concentration within the reactant phase will be 0. So, it maintains a maximum concentration gradient across the between the internal phase and the external phase. On the other hand, in type 2 or type of facilitation, the transport of the solutes will be facilitated by a complex formation, that is by a reagent present in the oil phase. So, therefore, the concentration of the solute becomes 0 even in the oil phase. Therefore, it gives a maximum concentration difference between the interface of the external phase and the membrane phase or the oil phase. Then the solute will be transported by the complex, because the complex cannot diffuse out of the oil phase, because it does not like the aqueous phase, it is hydrophobic in nature. So, it will be still remaining in the oil phase, and since its concentration is maximum, it will move into the internal phase. At the internal phase, oil phase interface, it will release the solute, and solute will move into the internal phase, where its concentration will be 0, because it reacts with the reagent present in the internal phase. So, that is the type 2 of facilitation. Now, what we will be doing in this class, we have started began the initial things of the modeling of the type 1 facilitation, which are most common in liquid emulsion membrane. We will do it once again and finish this type of modeling of this type of facilitation. So, we will look into the modeling of batch extraction by liquid emulsion membrane, and mainly we will be talking about type 1 facilitation. Okay. Now, we will be talking about some general features of this type 1 of facilitation. Features. In fact, the features that we are talking about, they are absolutely general. Some of them may be present in a particular system, may not be present, that we will discuss in detail. Solute A from external phase diffuses to the internal phase, and there it reacts. After reaction, it becomes species B. A becomes B. A does not exist, so it becomes B, and the transport of the solute A from the external phase to the internal phase will be quantified by a mass transfer coefficient Ka. Okay. So, Ka is mass transfer coefficient that accounts for transport from external to internal phase. Okay. Second point is that B diffuses to the external phase. Okay. So, B is formed in the internal phase, it diffuses to the external phase by two mechanisms. Okay. What are these mechanisms? The first mechanism is it diffuses through the oil phase. Diffusion through the oil phase, this through via and this will be quantified by a mass transfer coefficient K b. Now, K b may be 0, K b may not be 0. If the complex that is produced that is entirely hydrophilic or ionic in nature, it does not like the oil environment. So, it may not be diffusing through the oily membrane. So, in that case K b will be equal to 0, that means it may or may not. Okay, it is most general. Second mechanism is mechanism 2 is that the solute B, the complex that is formed B, it can come to the external phase via breakage of the membrane, breakage of the emulsions. Okay. Breakage of emulsions. Suppose some of the droplets or emulsion droplets they break, okay, then obviously the whole thing will come out in the solution. Okay. And this breakage is quantified by a coefficient called breakage coefficient, and it is denoted by phi. Like the diffusion is quantified by mass transfer coefficient, similarly the breakage is quantified by breakage coefficient phi. Third salient feature is in external phase B again converts to A. B can get converted to A. I will give an example. Suppose A is phenol, okay, and the internal phase you contain sodium hydroxide. So, phenol diffuses through the oil phase or the membrane phase into the internal phase, it produces sodium phenolate, and by somehow either breakage mechanism or by the diffusion mechanism, sodium phenolate comes to the external phase. Now, if the external phase contains sulfuric acid, then again sodium phenolate will react with sulfuric acid and produces phenol once again, and sodium sulphate will produce. Okay. So, therefore, it is highly possible. So, there is a general thing. Now, in the external phase sodium sulfuric acid may be present or may not be present. So, that depends on your choice. Suppose you are talking about acidic effluent, the sulfuric acid may be present, otherwise it may not be present. If it is present, you can convert back some of the B into A, but that proportion will be much less. Suppose it comes to the external phase only by breakage, since the breakage amount is very less, the amount of phenol producing back in the external phase will be less in presence of sulfuric acid. Number 1, sulfuric acid may not be present at all. Okay. So, in general, if it is present, then in external phase B can get converted into A. So, therefore, so what is the conclusion about these three salient features? A can exist only in external phase. A cannot exist in internal phase because it will be basically B. A can exist only in external phase, number 1, and B can exist only in internal phase, because if B comes out somehow either through breakage or through diffusion or by the both mechanisms into the external phase, B will be converted again into A. Okay. So, B in its form can present only in internal phase. Okay. So, this whole mechanism can be schematically represented as by this. Suppose this is the liquid membrane, this is the emulsion droplet. There is basically double emulsion, one droplet is formed inside, that is the internal reagent, another one is the external reagent, and let us say A is phenol, okay, it is present in the external phase, and the external phase let us say it is a sulfuric acid solution, and internal phase is nothing but NaOH solution. Okay. So, A turns into the A moves into the from external phase into the internal phase, then immediately it forms with sodium hydroxide sodium phenolate. Okay. So, sodium phenol, and this transport is quantified by Ka, and this sodium phenolate can go out either by Kb and some amount of breakage, and then when it comes into the external phase it immediately reacts with, and this B is produced there, and B is nothing but sodium phenolate. If A is phenol, then B is sodium phenolate. And when B comes out to the external phase, it again reacts with sulfuric acid and produces phenol back. Okay. So, this again produces A. So, the whole thing now what I am saying that Kb may be equal to 0 if the species B does not like the hydrophobic environment. So, it cannot diffuse through the oil phase, this is the oil phase, oil or membrane phase. Okay. This is the internal phase, this is the external phase. Okay. So, now we will go into the go into more details. Now, let us try to quantify breakage. Breakage of internal phase is assumed to be proportional to rate of breakage of internal phase, breakage of internal phase is proportional to volume of internal phase at any point of time, at any time t. That means, if the volume becomes larger, it becomes unstable. So, there is more possibility of breakage. Okay. So, this is mathematically written as minus dvi dt is equal to phi times Vi. Vi is the volume of the internal phase, and minus dvi dt is rate of decrease of the internal phase with a proportional constant phi. So, you can integrate this out. So, upon integration, what you can get is that you will be getting the expression of volume of internal phase at any point of time as V I naught exponential minus phi t. Okay. V I naught is the initial volume of internal phase. Okay. Now, the total volume of the system can be written as V naught as V E naught plus V I naught, that is initially. So, this is initial total volume, V E naught is the volume of the external phase initially, V I naught is the volume of internal phase initially. Okay. Now, at any point of time, V naught, the total volume will remain same, right. V naught will be is equal to V E plus V I. V e is the external phase volume at any point of time, V I is the internal phase volume at any point of time. Now, if we have an example of phenol plus H2SO4, so now let us look into an example phenol plus H2SO4 as an internal phase, as an external in external phase. They are present in external phase. Okay. And internal phase contains the aqueous solution of sodium hydroxide. Contains the internal phase. So, what happens in internal phase after diffusion of phenol into internal phase, it produces sodium phenolate. Sodium phenolate is produced in internal phase. Okay. Now, some amount of sodium phenolate comes to the external phase via breakage. Okay. So, it does not like the oil phase, so it does not come out by diffusion, okay. But some amount of sodium phenolate comes out to external phase via breakage, okay. And this then in external phase reacts with sulfuric acid and produces sodium sulphate plus phenol again. Therefore, concentration of A in internal phase is always 0. The internal phase A does not exist, it produces sodium phenolate. So, CIA is equal to 0 always. And what is CIA? Concentration of A in internal phase. Okay. That simply means A exists only in external phase, and concentration of B in external phase is 0. CEB is equal to 0, because whenever B comes out in the external phase, it immediately reacts with sulfuric acid. That means B exists in internal phase only. That means if this mechanism prevails, that sodium phenolate comes out to the external phase by breakage only, therefore, Kb will be equal to 0. That means, sodium phenolate, which is B, cannot get transported to external phase by diffusion. Okay. Because the sodium phenolate being an ionic species, it cannot diffuse through the oily phase, that is the membrane phase. So, therefore, in that case Kb will be equal to 0. Okay. Next, we get the concentration profile. For the concentration profile, in order to obtain the concentration profile, we have to do the material balance equation. So, balance equations, you can write balance equation in external phase if we write down the balance equation in the external phase, it will be d dt V e times C E A. So, this is basically A balance, my solute balance. So, rate of accumulation will be is equal to net rate in minus net rate out. So, that is true for any balance equation, whether it is a species balance, whether it is energy balance, whether it is momentum balance, whatever. So, this will be equal to minus Ka naught, okay, we put it Ka, let us say Ka CEA plus phi Vi CIB. Okay. So, some amount of A will be going into the internal phase via the mass transfer coefficient Ka, and some amount will be coming out because of the breakage. At time t equal to 0, CEA will be is equal to CEA naught and CIB is equal to CIB naught. Okay. Now, overall solute balance that you can do. So, this is a species balance equation. You can do overall solute balance in the specific example that we have talked about phenol and sulfuric acid and NaOH. At time t is equal to 0, there was no CIB naught, because sodium phenolate was not present from the very beginning. I am just writing the general equations and general conditions. Okay. So, in that particular case, CIB will be equal to 0 at time t is equal to 0, because there is no formation of phenolate there. The species B was not present at all at time t is equal to 0. It produces once A will be diffusing into the internal phase. So, overall solute balance will give you total solute mass at A at t is equal to total initial mass. Total solute mass at any point of time is equal to total solute mass at t is equal to 0. So, mass balance will be always maintained. So, therefore, this can be written as Vi CIB plus VE CEA is equal to VE naught CEA naught plus VI naught CIB naught. That means, CIB naught may be 0, okay, that is fine, and B will be present only in internal phase and A will be present only in external phase. Okay. Now, expression of species B is then obtained. You can obtain the concentration of species B. It will be 1 over VI VE naught CEA naught plus VI naught CIB naught plus minus VE by VI CEA. Okay. So, you will be getting the expression of CIB at any point of time. Now, let us talk about two situations. In one case, breakage is small, another case breakage is large. In fact, breakage is generally small. Our aim is to have the small breakage, to control the breakage as low as possible. Now, therefore, we talk about the for small breakage only. Otherwise, only for the small breakage you will be getting an analytical solution. For larger breakage you will be getting a complicated expression. Okay. And we basically looking for small breakage only. And small breakage, what do you mean by the small breakage and the larger breakage? These will be characterized by phi should be less than 1.4 into 10 to the power minus 5 second inverse. When phi is less than this value, we talk about the breakage will be extremely small. So, if breakage is small, the change in internal phase volume is less than 5%. Okay. So, how this value you are reaching? You are reaching this value, so that the internal phase volume changes, that means reduces, changes means reduces, changes by 5% only. Okay. So, that means if you put this value it will be 5% only. So, we are saying that if there is a change in volume of internal phase by 5%, the change is negligible. Okay. So, under this situation you can consider, it can be, there are two assumptions and these are crucial assumptions. You can make these assumptions which are very valid now. VI will be roughly equal to VI naught, okay, because there is no change in volume of the internal phase as well as external phase, because the change is really insignificant. Okay. And VE will be roughly equal to VE naught. Now, under this situation you can get the expression of concentration of B in internal phase as CIB is equal to VE naught divided by VI naught CEA naught plus CIB naught minus VE naught V I naught C E A. Okay. Fine. Now you can substitute this expression into the governing equation of species mass balance of A. Substitute this in differential equation, that is the governing equation of A. If you do that, what you will be getting is that d C E A dt will be minus K A divided by V E naught times C E A plus phi times V I naught divided by V E naught C I B. So, this will be minus K A V E naught C E A plus phi times V I naught divided by V E naught. Just substitute the expression of C I B, V I naught C E A naught plus C I B naught minus V E naught divided by V I naught C E A. Okay. So, finally, you will be getting this expression minus, I am just opening this bracket up, that will give you something that I will discuss, K A minus K divided by V E naught times C E A plus phi V I naught will be cancelling out, and so you will be getting phi times C E A naught plus phi times V I naught divided by V E naught C I B naught minus phi times C E A. Now, this equation, if you see that this equation can be written in this form, on simplification you can write d C E A dt plus alpha times C E A minus beta will be equal to 0, where your alpha is equal to K A divided by V E naught plus phi, and beta is equal to phi times C E A naught plus V I naught divided by V E naught C I B naught. Okay. So, this will be the simplified version of this equation, and all these initial values are known, and k and phi are the two parameters. Now, what is this equation? This is is this a homogeneous or non-homogeneous equation? This is a non-homogeneous ordinary differential equation of order 1. Okay. So, first order non-homogeneous ordinary differential equations, and it will be, its solution will be constituted of two parts. One is the homogeneous part, another is the particular integral, right. Homogeneous solution plus particular integral. Let us look into the homogeneous part and the particular integral both. The homogeneous solution gives d C E A, let us say H is homogeneous, dt plus alpha C E homogeneous is equal to 0, and the solution is C E A homogeneous part is some constant k 1 exponential minus alpha t, right. That is the solution of this, and let us look into the particular integral. The particular integral will be C E A particular will be nothing but beta by alpha. How did you get it? If it is a constant part, if the homogeneous part is constant, then you have to put the whole solution there and see what is the constant part, homogeneous, non-homogeneous part. So, non-homogeneous part comes out to be this. So, the total solution will be nothing but linear superposition of the homogeneous solution and the particular integral. If you forget about how to evaluate the non-homogeneous solution of partial differential or ordinary differential equations, just look back into Kreyszig and get it rebrushed. Okay. So, the total solution will be nothing but a linear superposition of the homogeneous part and the particular integral, and this becomes CEA plus CEAH plus CEAP, and this becomes K1 exponential minus alpha t plus beta by alpha. Okay. So, at time, and the initial condition was at time t is equal to 0, my CEA was is equal to CEA naught. Okay. So, you can find out the integration constant and you can substitute there, and the final, I am just writing the final form of the solution. The final form of the solution becomes CEA at any point of time is equal to CEA naught exponential minus alpha t plus beta by alpha 1 minus e to the power minus alpha t. This gives the final solution of this particular situation when the breakage is small. Now, let us look into the case number 2 where the breakage is reasonably large. Okay. Breakage and how the system will the solution will change. Now, in this case the variation of internal volume becomes significant compared to the earlier case where it was insignificant. So, variation of internal phase is significant. And what is the variation of internal phase? The variation of internal phase will be nothing but V I is equal to V I naught exponential minus phi t that we have described earlier. This is the way how the internal phase varies with as a function of time with the breakage constant phi. So, time variation of external phase is what? Time variation of external phase becomes V E is equal to V naught minus V I naught exponential minus alpha t minus phi t, right. So, we know that total volume was V E plus V I naught. So, we just put the V naught is equal to V E plus V I, just substitute the expression of V I, you will be getting the variation of external phase at any volume at any point of time. Now, once you get this, you can do an overall material balance and can obtain the expression of B, expression of concentration of B in the internal phase. Write an overall material balance in both the phases like whatever you have done earlier, exactly like that, and get the expression of concentration of B in internal phase. That means, you are looking for an expression of CIB. Okay. So, CIB becomes in this case V E naught divided by V I C E A naught minus V I naught divided by V I C I B naught minus V divided by V I C E A. Okay. So, now I am going to substitute the expression of V I as a function of t. Okay. So, if you do that, so what you will be getting is 1 over V I naught e to the power minus phi t bracket V E naught C E A naught minus V I naught C I B naught minus V naught minus V I naught e to the power minus phi t times C E A. So, what is this? This is nothing but the volume of the external phase at any point of time. Okay. Now, you do the species A balance. Do a species A balance and you will be getting the time variation of concentration of A in the external phase. So, d dt of V E C E A, that is the net rate of accumulation, is equal to minus K A C E A plus phi V I C I B. So, that is the rate by which it is coming out, and that is the rate by which it will be going into going into the from the internal phase into the external phase. Now, you just substitute the expression of C I B from here to here, and that will be a function of time, etc. So, the final expression will give you. So, combine last two expressions. Okay. So, what we will be getting is C E A d V dt plus V E d C E A dt is equal to minus K A C E A plus, this is on the right hand side, plus phi V I e to the power minus phi t divided by V I naught e to the power minus phi t V E naught C E A naught minus V I naught C I B naught minus V naught minus V I naught e to the power minus phi t C E A. Okay. And what is dV dt? We know the expression of V from the overall volume external phase volume balance. V is nothing but V naught minus V I naught e to the power minus phi t. Okay. So, you can find out what is dV dt. dV dt is nothing but V I naught phi e to the power minus phi t, correct. So, that I am going to substitute here, and so and you can take it on the other side. So, you will be getting d C E A dt as a function of C E A and of course time. So, you will be getting a form of this ordinary differential equation, but the form is such that we cannot have an analytical solution in this particular case, and this has to be solved with the initial conditions at time t is equal to 0, C E A is equal to C E A naught. Okay. So, once so it's basically an ordinary differential equation. It is an initial value problem, and this has to be marched forward using Runge-Kutta-4 or Euler's method or any other suitable numerical technique for solution of ordinary differential equation. Okay. Next, we calculate what is the amount of consumption of chemical reagent in external phase. That is quite important, because this process will be very efficient when you will be maintaining the maximum concentration difference, concentration gradient. That means, solutes will be going into the internal phase, reacts with the internal phase, its solution, its its concentration becomes 0. So, you can maintain the maximum concentration difference, but there is some limitation, because you have the limitation of the external reagent, the internal reagent. Okay. So, suppose all the reagents will be consumed, then this process will be coming to a stop almost, okay, because the concentration gradient will be decreasing and after some time it will be stopped. So, it is very important to quantify the amount of chemical reagent that is present in the internal phase or external phase to so that the things will be going on. Okay. So, consumption of sulfuric acid, I am talking about the example of phenol and sodium, phenol sulfuric acid system with the sodium hydroxide as an internal phase. Consumption of sulfuric acid in external phase is the amount required to convert phenolate to phenol through, what is the mechanism? Through breakage only, through breakage of internal reagent, that means containing sodium phenolate okay. And this amount will be given as by this expression integral 0 to t phi v I c I b plus phi v I c I r dt. What is CIR? CIR is the concentration of internal reagent. Why these two terms will be coming? This first term will be coming since there is a breakage. So, breakage of phenolate into the external phase. This term represents breakage of phenolate to the external phase. And what is this term means? This term means that internal phase itself leaks. Some amount of internal phase itself leaks containing the sodium hydroxide that directly comes to the. So, whenever there is a breakage, not only the sodium phenolate will be present, some amount of sodium hydroxide will also be present, because not all the sodium hydroxide will be converted into phenolate. Okay. So, both of the terms will be present. This comes because of the sodium phenolate will be coming into the external phase, and this term is because of the sodium hydroxide or the internal reagent will be coming out because of the breakage to the external phase. Now, we can do an balance on the internal phase, internal reagent. Balance of on internal reagent will give you this ordinary differential equation d dt of V I C I r is equal to minus k a C E a plus phi V I C I r. Okay. Now, again we will be considering two cases, small breakage and large breakage. For small breakage, we can consider V I is independent of time. Okay. So, and it is equal to V I naught, as we have done earlier. V I will be roughly equal to V I naught, and similarly V will be equal to V E naught. Okay. So, d C I r dt will be minus k a divided by V I naught C E a plus phi times C I r. So, you will be getting d C I r dt plus phi C I r is equal to minus k a V I naught times C E a, and substitute the expression of C E a here, that we have already known, C A naught e to the power minus alpha t plus beta by alpha 1 minus e to the power minus alpha t. We just substitute the solution of C E a that we obtained earlier for the case of small breakage. Okay. So, this becomes d dt of e to the power phi t C I r is equal to minus k a divided by V I naught C E a naught e to the power minus alpha minus phi t plus beta by alpha e to the power phi t minus e to the power minus alpha minus phi t. So, anyway, again you will be having a non-homogeneous set of equation, and at time t is equal to 0, we consider C I r is equal to C I r naught. Okay. So, the integration of the earlier equation will give you C I r is equal to minus k a divided by V I naught into beta by alpha phi minus e to the power minus alpha t over alpha minus phi C e a naught plus beta by alpha phi bracket close plus k. This is a constant of integration. This constant of integration can be evaluated once you use the initial condition, and this k turns out to be C I r naught plus k a divided by V I naught beta by alpha phi minus 1 by alpha minus phi C e a naught plus beta divided by alpha phi. Okay. So, one can get the W e is the consumption of external phase as integral 0 to t phi V I C I b plus phi V I C I r dt. We know the expression of V I. Okay. So, since it is small, the breakage is small, V I will be equal to V I naught, and we know the expression of C I b earlier, and right now we have derived the expression of C I r as a function of time. That has to be substituted here, and this integral has to be evaluated numerically. Okay. So, you can find out the consumption of external phase. Similarly, you can find out the consumption of chemical reagent in internal phase. Consumption of chemical reagent in internal phase can also be evaluated. That means W I, that means how much sodium hydroxide has been consumed to convert phenol into phenolate. Okay. So, W I, the internal phase will be integral 0 to t K A C E a plus phi V I C I r dt. Okay. We know the expression of C E a, we know the expression of C I r, we just derived it, and V I will be equal to V I naught, and we can evaluate the amount that is consumed for the of the chemical reagent in the internal phase. And remember, V I will be equal to V I naught for breakage is small. Next is case 2, when we are talking about large breakage. In the case of large breakage, what we have to do, you have to assume that the breakage rule, that V I will be reducing as a function of it is proportional to the volume. So, V I naught e to the power minus phi t, and V e will be nothing but V naught minus V I naught e to the power minus phi t. So, again you have to do the same balance equations that whatever we have done earlier, and substitute this there and redo the calculations. Basically, it will be exactly the same thing whatever we have done earlier. Okay. And you will be getting an, again the solution will be numerically obtained, it will not be analytical in nature. Okay. So, that is roughly how we will be calculating various quantities and how we will be modeling. So, once you can do small, because you do not know the value of phi and K a priori. Okay, you do not know these values. So, what you have to do? You have to do small scale experiments for a particular system and get the concentration profile. That means, you measure the concentration of the particular reagent in the external phase, get the concentration profile, and then you know the numerical solution, the analytical solution. So, you start with a guess value of K a and phi, these are the parameters, and calculate the concentration profile theoretically with the guess set, and check whether this calculated profile matches with the experimental profile or not. If not, then you redo you do the re-guess the set of the parameters, values of the parameters, and how it will be done? It will be done by an optimizer. So, your main subroutine has to be hooked up with an optimizer that will automatically select the next set of parameters values, and it will calculate the profile once again and see the sum of the squares is minimum or not. Okay. Now, let us look into one example of this. So, once you know the value of Ka and phi for a particular system using a small scale experiment, then you can go for the large scale experiments in the predictive mode, because this phi and K will be invariant for this particular set of system. So, you can go for the scaling up. Now, we will look into an example of liquid membrane. Phenol is removed, in an emulsion liquid membrane system. Let us say from its initial concentration of 10 ppm. ppm is nothing but milligram per liter. The volume of external phase, that is sulfuric acid, is 50 ml. Okay. We started with 50 ml, and that of internal phase that is NaOH is 10 ml. Okay. So, initial values are given, and internal reagent concentration initially was 6 ppm. Internal reagent concentration at T is equal to 0 was given as 6 ppm, 6 milligram per liter. The breakage coefficient is given as 10 to the power minus 5 second inverse, and Ka is given as 10 to the power minus 3 milliliter per second. So, what we have to do? We have to find out phenol concentration in the bulk phase, that means in the external phase after 5 hours. What is phenol concentration in external phase, let us say after 5 hours. Okay. So, the solution is straightforward. So, we just write down the expression of CEA. CEA is the phenol concentration in the external phase at any point of time. CEA naught e to the power minus alpha t plus beta by alpha 1 minus e to the power minus alpha t. So, this gives you concentration of phenol in external phase at any point of time. Okay. So, and what is alpha? Alpha is Ka by V E naught plus phi, beta is equal to phi C E A naught plus V I naught by V E naught C I B naught. Okay. So, phi, the breakage coefficient is given is 10 to the power minus 5 second inverse. A is phenol. So, we denote phenol as A. So, CEA naught, the initial concentration is 10 ppm, VE naught, that is the volume of external phase, initially was 50 ml, VI naught is given as 10 ml, Ka is given as 10 to the power minus 3 milliliter per second. So, now we calculate various quantities. So, once we give all these values, we calculate the value of alpha, it is 10 to the power minus 3 by 50 plus 10 to the power minus 5, it turns out to be 3 into 10 to the power minus 5 second inverse. Beta turns out to be 10 to the power minus 5 into 10 plus 10 by 50 into 6. Okay. So, it is 11.2 into 10 to the power minus 5, and CEA is given as 10 e to the power minus 3 into 10 to the minus 5 times T plus 11.2 into 10 to the power minus 5 divided by 3 into 10 to the minus 5 into 1 minus e to the power minus 3 into 10 to the minus 5 T, and we are going to find out what is the value of T at 5 hours. So, T is equal to 5 into 3600 second, and CEA turns out to be 7.38 ppm. Okay. So, it gives some value. So, with a judicious selection of K and other things, Ka and B phi will be depending on the selection. K will be depending on the selection of oil phase and the external phase, number 1, and phi will be depending on the stirring that you are going to have in the system. Okay. So, whether and also the surfactant gives the stability of the emulsion, whether the surfactant is good enough or efficient enough to stabilize the surfactant, so that the breakage will be or leakage will be minimum. Okay. So, for different various values of parameters, one can estimate or model these systems. I have just given one simple calculations, but these systems are right now much used in separation of separation of oily water, separation of waste stream containing the organics, containing the inorganics. It is extremely useful when you are having small concentrations of metal ions, for example, cadmium, zinc, arsenic and lead, so on and so forth. So, this method is also, liquid membrane is also used not only for the separation, but to concentrate the metal ions. It can be used for the analytical purposes. What is the analytical purpose? Suppose you are having a very dilute stream of lead or cadmium, which is very dangerous. Okay. But you cannot measure its value, its concentration, because lower be the concentration, any instrument will be erroneous in nature. It will give erroneous results. The uncertainties over the measurements becomes large when the concentration becomes lower and lower. So, what it is done for the analytical chemists, try to concentrate it. This is one of the method they used. The cloud point extraction is another method, liquid membrane is another method in the analytical chemistry to extract the concentration of the cadmium or lead, the dangerous material or the metal ions, into a phase where its concentration becomes more. So, it can be detected much more easily. Okay, detection or measurement becomes much more efficient. So, that is for the analytical chemistry. Apart from that, these liquid membranes can be used for purification and the treatment purposes as well. But the point is, the stability of the liquid membrane has become a problem, and it is really a problem for to have a stable emulsions beyond half an hour, even 45 minutes, 1 hour. I am saying 5 hours for this particular example. I have given 5 hours, that is too large, too optimistic a value. Okay. Generally, liquid membranes, the emulsions are not stabilized to that extent. So, stability of the liquid membranes is one of the major problem that basically hinders its widespread applications industrially. Okay. So far, we have just come to the end of the third surfactant mediated separation process, that is a liquid membrane system. In the next class, we will move on to centrifugal separation processes. Thank you.